Okay, so let's begin. Let me start by reviewing a couple of definitions from the last time. So we were studying the measures for of distance sort of between quantum states. So we saw one definition in detail, which was the trace distance. And if you remember, the classical trace distance was defined as, let's say we have two probability distributions PM, QM, then the classical trace distance was defined as half sum over absolute values of differences between corresponding probabilities of the probability distribution. And the quantum trace distance between two mixed state in general, rho and sigma, was defined as half trace of rho minus sigma, where the modulus of the positive of an operator was defined as the positive square root of this operator. And we saw a couple of properties of this distance, and one was that if we have a set of measurements operator EM, POVM measurements, then the trace distance, quantum trace distance between two states is bounded by the classical trace distance between the two probability distributions that are generated by the measurements of rho and sigma. Okay, and there was another, I think, important property that we saw, that for the trace preserving quantum channels are contractive. Contractive mean that when two states pass through the same quantum channel, the distance between the states can only decrease, it cannot increase. So that the term that we use for it is that they are contractive. And also there was triangular inequality. That this distance is always greater than from the distance between rho and tau. So these were a few things that we studied about the trace distance, and then we also studied the second definition, which was let me define it here, the fidelity. And we defined the classical fidelity as between two, distributions like this, and the quantum fidelity was defined as trace of p square root sigma, sorry, not p but rho square root. And actually I'll show today that this is equal to rho square root, sigma square root rho sigma square root. I'll show it a little bit later. So this was the definition for fidelity. And we took a couple of examples. We didn't study the general properties of fidelity, but we saw a few examples. I think one was for pure states, one pure and one mixed state. Let me see. So one example was when our states commute, then we saw that quantum fidelity is actually equal to the classical fidelity that is dependent on the eigenvalues of this rho and sigma in the same basis. If because when they commute, I can write rho as some Ri and sigma as some Si, and they are diagonalizable in the same basis. So this was one example. The second example that we saw was when one state is a pure state, another is something. So then we saw that the fidelity of a pure state and a mixed state was psi sigma psi. Was there a square root? Square root भी था. So this is what we had last week. So any question on this? आज हम जो है वो फिडेलिटी की प्रॉपर्टी स्टडी करेंगे, ठीक है, कुछ इसके एप्लीकेशंस और we will also see a dynamic measure of distance using fidelity. क्योंकि static है when we have like two states, we don't care where they're coming from, and we call the distance a dynamic measure when we are trying to compare the input and output state of a quantum channel or some other dynamical process. Somehow in the last few years, fidelity is becoming much more popular than the trace distance. So what we study here will have direct, applications in current research that is being done on quantum information and quantum computation. All right, so let's start with some properties. So number one, unitary operation doesn't change fidelity between two states. So for example, if you have some unitary operator acting on rho and this goes to rho dagger, and you have this unitary operation acting on sigma, and let's say go to your sigma u dagger, then we can easily show that the fidelity is the same as the fidelity between rho and sigma. So let me call it rho prime and this sigma prime. We can check the fidelity of rho prime sigma prime is इसका square root पहले लेना, trace of square root u rho u dagger, फिर sigma prime वैसे ही आ जाएगा, u sigma u dagger and then u rho u dagger square root and then whole square root. Okay, अब देखें ये हमारे पास जो है वो इस तरह से है, unitary operator rho unitary operator mod, and then we have some operation. So we can easily show that this operation actually transforms to this matrix, and so this is as it is, and similarly for this it's this, and this cancels out, this cancels because this is identity, and we have trace of u rho square root sigma rho square root u dash. और हमें पता है कि जो trace operation है cyclic. Trace of ABC is equal to trace of, you can bring the C here, CAB. लेकिन आप cyclically अगर change करते रहे, so this is the same thing. तो square root में भी doesn't matter because the you can imagine that if you diagonalize it in some basis, the square root transforms to the basis. So the same property is still applicable inside the square root as well. So this u dagger comes here, this becomes identity again. So this is equal to trace of rho square root sigma rho square root, which is fidelity of rho sigma. So unity operation doesn't change the fidelity, just like the trace distance. अगर आप याद करें तो जो trace distance है, that also didn't change after passing through a unitary channel. एक पहले क्या? हाँ हाँ. सो इसको ना देखने के दो तरीके हैं, ठीक है. एक तो आप इसको ये देखें कि जो स्क्वायर किसी ऑपरेटर का स्क्वायर रूट जो है वो ऑपरेटर होता है कि जिसको अपने से मल्टीप्लाई करें, यू गेट दिस थिंग. ओके, लेट्स से सो b square root is equal to b, that if I multiply b with itself I get what is inside the square root. ठीक है. अब अगर आप इसको लें, सो u rho u dagger, अगर इसको आप इसी से मल्टीप्लाई कर लें, and you see I get u because the identity है u rho square root rho u dagger, which is the same thing as in the square root. ठीक है. लेकिन दूसरा तरीका देखने का ये भी मतलब है कि you can diagonalize rho and write rho as something like some eigenvalue matrix and then some other unitary operator like this, क्योंकि इसको हम diagonal कर सकते हैं. And then जो इसको यहाँ पे रखें, so ये u dagger मिलके एक और unitary बन गया, ये और unitary बन गया, and then the square root only transforms to the diagonal entries. और उसके बाद you can plug back those unitary operator back in and you get to this thing. All right. और कोई question? Okay, so if not, I'm now going to prove one of the most important theorem. It's called Woolman Theorem. And before I do that, I need one quick result जो कि हम उसमें use करेंगे. So let me first derive that result. और मैं कुछ चीजें review करूंगा. Then I'll go to the Olman Theorem, which is regarding fidelity, or it's sort of one of the most important theorem concerning fidelity. अच्छा, इस theorem से पहले I need a couple of results. So let me start with result number 1 that I will use. And let's say we have trace of some operator A times some unitary and its modulus. And this operator A, any general operator A, can always be written as in a polar decomposition form like this, where this A is a positive operator defined as a dagger square root. Yeah, वैसे by the way, there are two polar forms. This is right polar form, and you can also have some left polar form like this, and where this A is now defined as a dagger A. Just to remember, जिस तरफ unity होता है उस तरफ dagger लगाना है. You can check its proof, in some linear algebra textbook. But the point is that any general matrix can be written as a positive matrix times a unitary matrix, or a unitary matrix times a positive matrix. And that positive matrix in terms of this is given by this. Okay, so this is called polar decomposition of any operator A. So let me write. Did he? I'll have to do some numerics. So कोई भी आप let's say कोई लिखे 2 by 2, and then you can find let's say by some elimination method, Gauss elimination, it's your method, say, as a set of operations that it will transform it into this thing. Okay, that you have a positive operator with positive eigenvalues, okay, or then some unitary operator. Okay, and so with polar decomposition, I can write this thing as some trace of a modulus, some unitary, like this. And then this can be written as trace of a mod square root, a mod square root, u prime u. Okay, मैं एक रिजल्ट निकालेगा इसका रिलेशनशिप. So I'm just rewriting it in different ways. इस मैंने लिख दिया. Now after this, I'm going to use Koshi Schwarz inequality. और अगर आपको, if you recall, the Koshi Schwarz inequality was like this. That's let's say I have two vectors u v. तो इनका जो inner product है उसका जो square है, this is always less than or equal to the inner product, the magnitude of u times the magnitude of v. ठीक है, this was the Cauchy Schwarz inequality. Or if we have some operators like a b, and then the inner product can be defined as, let's say, some a dagger b. This is equal to the magnitude square is equal to or less than trace of a dagger a into trace of b dagger b. So here inner product is defined as, ये वो Hilbert split inner product है between two matrices a b. So it's a dagger b, trace of a dagger b. So this is the inner product of matrices a b. So ये जो है, this is the Cauchy Schwarz inequality for Hilbert Schmidt operators. Okay, so with this thing I can now write this. आप इसको imagine कर लें, this is some a dagger and this operator is some b. So then this is less than or equal to square root of trace of a dagger, which is this, into a. और ये चूंकि पॉजिटिव ऑपरेटर है, हर्मिशियन ऑपरेटर, तो इसका a जो है वो भी वही होगा टाइम्स ट्रेस ऑफ ये b है, इसका डैगर क्या होगा, u डैगर u, क्योंकि ये पहले आ जाएगा, फिर इसका डैगर, फिर इसका जो डैगर है वो वही है, एंड देन दिस ओके. और इसको देखें, ये ट्रेस ए है, ए मॉड, और ये क्या चीज है, ये तो हो गया ना ए मॉड. तो ये जो कि साइक्लिक हम यूज कर सकते हैं, ये यू इधर आएगा तो यू डैगर आइडेंटिटी हो जाएगा, यू प्राइम इधर आएगा, यू प्राइम डैगर आइडेंटिटी हो जाएगा. सो दिस इज जस्ट ट्रेस ऑफ ए मॉड एंड दिस इज जस्ट ट्रेस ऑफ A mod. So it means that I have a result that trace of AU mod is less than or equal to trace of A mod. So this is just a mathematical identity. कोई भी ऑपरेटर A है उसके साथ कोई यूनिटरी ऑपरेटर मल्टीप्लाई हो रहा है, उसका जो ट्रेस का मॉडुलस है इट्स लेस देन और इक्वल टू द ट्रेस ऑफ द मॉडुलस ऑफ दिस ऑपरेटर A. दिस इज वन रिजल्ट जो हमें जो नेक्स्ट थ्योरम में प्रूव करने जा रहा हूं उसमें विल यूज. ठीक है मुनी, ये वाला जो ये देखें यहाँ पे मैंने कॉशी श्वार्ज इनइक्वालिटी इंप्लीमेंट कर दी. थिंकिंग ऑफ दिस एज ए डैगर एंड थिंकिंग ऑफ दिस एज बी. ठीक है, सो ए डैगर बी का जो ट्रेस है ट्रेस ए डैगर ए ट्रेस बी डैगर बी. तो ये ए डैगर है इसके साथ ए, क्योंकि ये पॉजिटिव ऑपरेटर है, ये हर्मिशियन है. ठीक है, क्योंकि पॉजिटिव ऑपरेटर की आइगन वैल्यू सारी रियल पॉजिटिव होती है, सो इट्स रियल, तो हर्मिशियन. तो ये आ गया. अब यहाँ पे पहले ये बी का डैगर होगा, तो डैगर लेंगे तो तरतीब उल्टी हो जाएगी, यू डैगर यू प्राइम डैगर ए मॉड, और फिर ये बी वैसे लिखती है. उसके बाद साइक्लिक प्रॉपर्टी यूज किया, ये यू इधर आएगा तो यू यू डैगर आइडेंटिटी, यू प्राइम इधर आएगा तो यू प्राइम डैगर आइडेंटिटी. सो जस्ट ए मॉड बचेगा. जो स्क्वायर रूट है दो है तो वो कैंसिल होकर तो ये आ गया. Okay, so let's now prove the theorem. It's called Woolman's theorem, and the statement is this: that suppose we have some general mixed states rho and sigma, then the fidelity between the state is a maximum over all possible purification of this rho and sigma, like this. Okay, so if you recall, अगर आपके पास कोई सिस्टम R है, ठीक है, and then let's say there is some state rho which is mixed state, we already know that we can have another system, let's say Q, of same dimension as R, and then this let's say this has some basis I prime I sub R prime. So I can write this rho as Pi I prime I prime R. So in this basis, we can diagonalize it, suppose like this, where this Pi is positive. This is that the Schmidt decomposition of this state. Now, if we have this mixed state, we can construct a corresponding pure state which corresponds to psi by bringing another system of the same dimension with R, and then writing this pure state over the whole two systems, which is given by Pi square root, and suppose I prime R is the basis for this, and some I, let's say this is system Q, I Q prime are the basis for the other system. So idea वही है, if you recall, कि ये ऐसी pure state है कि अगर इसमें से आप ये system trace out करें, you will get this state back. So this is the process called purification. So suppose for the state rho, there is a corresponding pure state psi, and similarly for the state sigma, there is a corresponding, suppose sigma is diagonalizable in some other basis, some, let's say Si, I double prime R, I double prime, sorry, I double prime R, and corresponding pure state is phi si square root I double prime r I double prime q. ठीक है, क्योंकि हम ये नहीं ले रहे कि रो सिग्मा कम्यूट करते हैं. They are not necessarily diagonalizable in the same basis. They are diagonalizable in the different bases but of the same system. हमें पता ना कोई भी वेक्टर स्पेस के अंदर we can have more than one basis. So maybe one state is diagonalizable in one basis, the other state is diagonalizable in other basis, and so on. But whatever the basis they are diagonalizable, we can always attach another system Q of the same dimension, and then we can choose. The theorem, purification theorem, says that there is some basis in this for each state that we can use to purify. So for example, for this, there is another basis I prime Q of this, which gives you this pure state. And for this, there is some basis I double prime Q, which gives you another pure state phi. So this theorem says that you have two mixed state rho sigma. You can prepare two pure states corresponding to them on a bigger system. And then fidelity is nothing but the magnitude of the inner product of those two pure states, such that you choose psi and phi in such that your inner product is maximum. Okay. It's sort of a simple thing, but it's very useful in proving many other properties later on. So one thing you can see right away that this tells us that the fidelity must be symmetric in psi and phi. क्यों? क्योंकि inner product को आप change भी कर दें, you still get the same number. वो complex तो आएगा, लेकिन चूंकि mod है, you get the same magnitude. So proof से पहले, does everybody understand what the theorem says? क्यों Abdullah? So it's just inner product of corresponding pure states, such that you choose these pure states in such a way that the inner product is maximized. All right. So let's now go for the proof. Now, before I go for proof, let me note one other thing, that I can write this state psi like this, that some unitary operator VR tensor with some with the square root of rho and some unitary operator UQ applied to this state M, where M is this special state, which is a tensor product of some two bases of system R and system Q. ठीक है? यानी R और Q की कोई एक basis आप ले लें, and they are not necessarily same as the basis in which your rho is diagonalizable. Okay, जैसे देखें ये prime है और ये without prime है. So these are some bases. तो उनको choose करके you construct a state M like this, which is sort of the maximally entangled state of these two things. Not maximally, unless you know it's true, but it's some entangled state. Okay, so first I'm going to show that you can write this pure state psi in this form. And then, this will be very easy to follow from that thing. Just to see that this is the same as that, we can see this thing. This is some unitary VR. This rho square root kya hoga? This rho square root is nothing but that thing, I, pi square root, I prime r, and then this some unitary operator UQ applied to this M state like this. ठीक है? अभी देखें ये जो ऑपरेटर है इसकी दो टर्म्स हैं. There is a tensor this thing and tensor that thing. So this applies to IR and all of this applies to, sorry, this is IQ. Okay, so this becomes just for simplicity, let me write this thing J now. Okay. Okay, दो sum है, एक ये भी sum है, एक ये भी है. And let me bring this sum out, sum over I here. And then I have this VR applies to IR. Okay. And this is just a number, so I can write it here, PJ square root. लेकिन चूंकि ये सम भी है, ये भी सम बाहर निकाल लेते हैं. सम ओवर I, sum over J, PJ square root. So VR applies here, and then ये जो चीज है, this applies there. And tensor J prime, and this UQ applies to IQ. Now suppose that I choose this unitary VR and this unitary UQ such that this is equal to I prime R and this is equal to I prime Q. So उस सूरत में क्या होगा? फर्स्ट यहां से एक चीज हम देखते हैं कि ये J प्राइम है, तो मैंने नोटेशंस उल्टी कर दी हैं. लेट्स if this p square rho square root is this side, then we should have expressed it in Q basis. And if this is on this side, then we could have expressed it in R basis. So in this case, let me express, this is on this side. So let's see, we are using this Q for the right side. So यहाँ पे आ जाएगा Q, ये Q आ गया. ठीक है, मैं जो right side system उसके लिए Q और left side के लिए R symbol use कर रहा हूँ. Anyway, so ये UQ इस तरह से है कि this UQI goes to I prime. So अब ये I prime और J prime, ये inner product जो है, this would be a delta function which is non-zero only when J is equal to I, which mean that the sum has non-zero term only for J is equal to I. So this becomes Pi square root. This is I prime R. Tensor ये delta function बन गया था, and then ये I prime Q. Yeah. So we see that this is just a special way of writing that pure state psi. ठीक है, वो जो pure state है R और Q के ऊपर, this can be written like this. ये जो सामने देख लिया, where these VR and UQ they are chosen such that you're able to transform this basis IR IQ to that I prime R and I prime Q basis. जी कौन सा वाला? ये वाला. तो लेट्स चूज दिस, ये UQ जो है ना इस पे ऑपरेट होगा ना दूसरे वाले पे. ठीक है, क्योंकि ये टेंसर के बाद वाला ऑपरेटर है. सो दिस ऑपरेटिंग ऑन द सेकंड वन, और जो ये ऑपरेटर है ये इस पे ऑपरेट हो रहा है. तो VRIR आ गया, and all of this is operating on this. So this UQ is operating on IQ. तो हमने कहा कि let's choose this UQ such that UQ IQ is I prime Q. Okay, that this UQ is such that it transforms this basis into this basis, जिसके अंदर आपने ये रो को लिखा हुआ. तो उससे क्या होगा कि ये जो inner product है, then this will become a delta function because these are orthonormal bases, so which is non-zero only when I is equal to J. So the sum over J goes away and only sum over I is left, and then this VR is chosen such that VRIR is sum I prime R, and we get the same state as psi. So the point is that by choosing this VR and UQ in special ways, we can write the pure state like this. Okay, so once we have this thing, I can similarly say that I can choose the state So let me use let's say symbol u here and u here, and for phi some vr sigma square root some vq. So ये psi के लिए u's हैं और phi के लिए v's हैं. So इसी तरह इसके लिए भी कोई unitary operator choose करके I can convert that pure state into this form. Now we have this thing, and we can now prove the theorem very easily. That let's see what this quantity is now. जो वो theorem में right side पे quantity है. So it should be, you know, the modulus of that thing. वो क्या चीज है? M. Phi में आ जाएगा M, and we have we are daggered. ये कौन सी स्टेट है? ये है phi. So I'm switching M, and then the VR, and this is VR dagger, and then I have UR, right? So ये आ गया यहाँ से. So this M comes coming from the other side, and then this is the operator on the left part, and then this is the operator on the left part. So we get VR dagger UR tensor. जी जी, पहले हम, अच्छा एक मिनट मैं लिख लूं फिर देख लेते हैं. UQ dagger rho square root sigma square root VQ. हाँ पहले साई ले रहे हैं. सो साई का भी इधर एम ही पहले ये आ गया, एंड देन वी हैव इस तरह से लिख लेते हैं. पहले साई को लिखते हैं. क्या होगा? साई स्टेट होगी एम, और एम के ऊपर जो ऑपरेटर है वो क्या है? यू आर डैगर टेंसर यू क्यू डैगर रो स्क्वायर रूट. ठीक है. ये देखिए जब हम इसको रिवर्स कर ले तो इस तरह से कर रहे हैं. एक ये स्टेट है, सो दिस कम्स हियर, और जो ऑपरेटर है उसका भी हमने डैगर लेना. सो ऑपरेटर का जब डैगर लेंगे, सो ये याद रखना है कि जब टेंसर प्रोडक्ट पे सारे का डैगर ले रहे होते हैं तो उसको ये नहीं करते, यानी इसका जो डैगर है इट्स नॉट लाइक दिस. सो ये क्योंकि जो लेफ्ट वाला ऑपरेटर है वो लेफ्ट वाली क्यूब, यानी इस तरह से स्टेट है ना. तो जब हम डैगर ले रहे होते हैं, सो इस ट्रांसपोज लेते हैं तो ये बन जाती है स्टेट, ये एक्स वाई है. सो दिस बिकम्स एक्स वाई. तो जो लेफ्ट पे स्टेट है वो लेफ्ट पे ही रहती है. ठीक है. जो राइट पे स्टेट है वो राइट. तो इसी तरह जो ऑपरेटर्स हैं इनका भी जब डैगर लेना है तो ये लेफ्ट वाला ऑपरेटर लेफ्ट पे ही रहना चाहिए और राइट वाला ऑपरेटर राइट पे. तो इसका डैगर यानी यूं आ जाएगा टेंसर दिस डैगर. ओके. सो वो मैट्रिक्स मल्टीप्लिकेशन वाला हिसाब नहीं करना कि मैट्रिसेस को चेंज कर देना. जो मैट्रिक्स मल्टीप्लिकेशन फिर डैगर में स्विच करना है, लेकिन टेंसर के अक्रॉस स्विच नहीं करना. तो इसी तरह जो साइज स्टेट है वो ये बन जाएगी. अब हम देखते हैं कि ओके, सो ये आ गया. हाँ ठीक है, यहां पे आएगा यू आर डैगर ये वाला, और उसका आ जाएगा बी। ठीक है, ये बनेगा क्योंकि यहाँ पे ये इधर आ गया और जो उसका राइट वाला वो यहाँ पे आ गया। ऑल राइट, ये आ गया हमारे पास। अब there's another identity that I need, which you can easily prove, that trace of A dagger B is A tensor B M. You can actually show very easily. ये A कोई मैट्रिक्स लें, B कोई मैट्रिक्स लें, उनका टेंसर प्रोडक्ट लिखें, तब उनको अप्लाई करके you take the this product, and then if you take A dagger B and multiply take trace, they both are the same. So this is a mathematical identity which I can use here, which means that this is equal to trace of, इसका dagger लेना, ये जो ऑपरेटर है इसका dagger आ जाएगा VR dagger UR, and then ये वाला ऑपरेटर UQ dagger rho dagger sigma dagger VQ. ये आ गया हमारे पास। Okay, now what I can do, that I can transform all of these unitary operators to this side. ये पहले ये वाला, फिर ये वाला, फिर ये वाला, and then I will get here VQ VR dagger UR UQ dagger. Let me call all of it some U. So this becomes trace of rho square root sigma square root U. Okay, क्योंकि जो trace operator है इसमें we can cyclically change the position of the operators. So this is this, और जो वो हमने शुरू में result एक prove किया था, this modulus is always less than or equal to the trace of modulus, right? तो उसमें हमने इसको A कहा था, sum operator A time unitary, trace का modulus, so it's equal to trace, it's less than or equal to trace of the modulus of this operator. और जो ये चीज है, let's see what this is. So ये किसी ऑपरेटर का मॉडुलस है, तो ऑपरेटर का मॉडुलस जो है वो हमने किस तरह से डिफाइन किया हुआ है, इट्स दिस थिंग, सो ए मॉड इज ए डैगर ए, सो इसका डैगर आ जाएगा सिग्मा स्क्वायर रूट रो स्क्वायर रूट, और फिर ये वैसे आ जाएगा रो स्क्वायर रूट सिग्मा स्क्वायर रूट और सारे का स्क्वायर रूट, एंड दिस इज ट्रेस ऑफ सिग्मा स्क्वायर रूट, ये रो बन जाएगा सिग्मा स्क्वायर रूट, एंड दिस इज दैट फिडेलिटी. I'll show a little bit later जो हमने वो definition की है जिसमें रो इधर आता है कि ये उसी के exactly बराबर है. So now we see that fidelity between rho and sigma is greater than or equal to this thing, which proves our theorem that you choose purified states psi and phi, then take their modulus. So this is less than or equal to fidelity of rho sigma, and equality occurs when it is maximized. And by the way, ये इसमें तो हमने इन दोनों को वेरिएबल रखा है. The proof can very easily be extended to the situation this way. We can say that psi is fixed. Psi is some fixed representation of purification of rho. Then this is equal to the maximization over phi. Yes, ulta bhi kar sakte. You can fix phi and then maximize over psi. So you don't have to maximize over both psi and phi. Even maximization over one can give us this equality. But in general, this fidelity is an upper bound to the magnitude of the inner product between the corresponding purified states of mixed states rho and sigma. So this is an alternative view of the fidelity between states rho and sigma. जी जी block sphere थोड़ा मुश्किल होगा unless it's a qubit state, but you know rho and sigma, they are some mixed state of some system, let's say R of some dimension D. Then you can bring in another system, let's say Q of the same dimension, and define a pure quantum state of that joint system. फर्ज करें आपके पास एक एटम है और उसकी कोई स्टेट रो है, you can, और वो मिक्स्ड है, you can bring in another atom and then you can define some hypothetical pure state of the two atoms such that your state rho is a traced out variant of that joint state. ठीक है, so theorem ये कह रहा है कि the fidelity of this subsystem states is an upper bound for the magnitude of the inner product between the corresponding pure state of those super systems, of those joint systems, bigger systems. जो रो और सिग्मा है, पहली बात है कोई एक ही सिस्टम की स्टेट्स है. whenever we talk about fidelity, we don't talk about the fidelity of let's say a state on apple and the fidelity of a state on an orange. जो प्योर है वो भी सेम सिस्टम की है ना, कि you have let's say a state rho and state sigma of an apple. You bring in another orange and you now have two systems but they have same dimension, and you then you purify your sigma states rho and sigma to a joint system, और वो सिस्टम दोनों का यानी हिल्बर्ट स्पेस दोनों की सेम है. क्योंकि जब भी हम कंपैरिजन करते हैं सिमिलर चीजों का करते हैं ना. वी कैंट हैव लेट्स से फिडेलिटी बिटवीन अ स्टेट, अ टू लेवल सिस्टम एक ले ले और एक थ्री लेवल सिस्टम ले ले, इसकी एक स्टेट है किसकी स्टेट है, उसमें फिडेलिटी वी कैन टॉक अबाउट फिडेलिटी बिटवीन दोस सिस्टम. ठीक है. Okay, so the next point that I want to show is something that we have used a couple of times, and it is the symmetry of fidelity, symmetry in rho and phi, that fidelity of rho and sigma is equal to fidelity of sigma and rho. In other words, I'm going to show the trace of rho square root sigma rho is equal to trace of sigma rho sigma rho. अच्छा, ये प्रूफ से पहले लेट मी जस्ट रिकॉल वन थिंग. जब दो चीजों का ट्रेस सेम हो, इट नेवर मीन्स दैट द थिंग्स आर सेम. ठीक है. अगर दो ऑपरेटर्स हैं ए एंड बी एंड दे हैव द सेम ट्रेस, वी कैन नॉट से दैट द ऑपरेटर्स आर द सेम. वी कैन से एनीथिंग, दे कैन बी सेम, दे कैन बी डिफरेंट. क्यों? क्योंकि ट्रेस में तो आपको पता सिर्फ डायगोनल एंट्रीज को ऐड करते हैं ना. वी डोंट से एनीथिंग अबाउट द ऑफ डायगोनल एंट्रीज. So when I say that trace of this thing is equal to trace of this thing, that is all that I mean. I don't mean that this thing is equal to this thing. सिर्फ हम ये कह रहे हैं कि इनका trace जो है वो बराबर है. Okay? And just to recall, how do we compute trace of some operator A? अगर कोई operator A है, तो in general, you know, it is, let's say, a matrix like this. So one way of finding traces, अगर आपको ये element का पता ही है, so you just go ahead and add them. But a systematic and usual way is this: when you don't have direct access to these diagonal entries, you go ahead and perform this eigenvalue expansions. Okay, so you actually perform the diagonalization of this operator A in some bases. Let's say some 3 and 2, so there are 0, so you just add these eigenvalues. Okay, so I can write an operator A in some eigenbases, then the trace is just the sum of these eigenvalues. Perfect. So it means if I have to show that the trace of this thing and that thing is the same, all I have to do is show that the eigenvalues of this operator and eigenvalue of those operators, they are same. And by the way, just here, अगर आपके पास कोई और operator है which has the same eigenvalues but different eigenvector, they will have the same trace. ठीक है? क्योंकि you just add eigenvalues, you don't do anything with the eigenvector. All right, so let's come here. अच्छा, उसके ये जो square root operator है, इसका trace and the trace of this thing is going to be the same, क्योंकि up to the square root, right? So if I can show that कि इसका और इसका trace same है by just square rooting, you can show that कि square root का trace भी same है. So I'm just going to work with this thing. So let's say that this operator has some eigenvector psi with some eigenvalue lambda. Okay. So this is an operator जिसका कोई eigenvector मैंने लिया है, उसकी ये eigenvalue है. Now what I do that I multiply on both sides with from the left with this operator. That let me call it let's put a sigma half and rho half from the left. और ये जो चीज है, let me write it, rho half, sigma half, rho half psi lambda sigma half rho half psi. ठीक, मैंने जस्ट इससे मल्टीप्लाई किया लेफ्ट साइड पे दोनों को. ये तो जस्ट सिग्मा को मैंने 2 दफा लिख दिया. Now what I can do that I can see that if psi is an eigenvector of this operator, then this thing, let me call it some psi prime, is an eigenvector of this operator because this is here and this is here. So इसका मतलब है ये वाला ऑपरेटर और जो ये ऑपरेटर है, they share the same eigenvalue but their eigenvectors are different. इसका psi prime है और इसका psi, which means that I can diagonalize this operator and let's say I get eigenvalues lambda i's. Then I diagonalize this operator and I get some eigenvectors. I will get the same eigenvalues lambda i's with different eigenvectors, which mean that, or similarly, if you talk about the square root, you know, the eigenvalues are square root of those eigenvalues, but they're still the same. Or which means that the trace of this thing is the same as trace of this thing. So fidelity is symmetric in its input states. जी? You might be right. Let's say कि हम ये phi और psi ले लेते. नहीं, इससे प्रूव नहीं होनी थी. इससे हम इससे करते तो इसमें हमने निकाला था वो रिजल्ट सिग्मा प्राइम सिग्मा रो सिग्मा, राइट? अगर उल्टा करते तो उससे आ जाना था रो सिग्मा रो. नहीं, ये तो हमने प्रूव ही नहीं ना किया इन जनरल. हमने वहां से चले रो साई और सिग्मा से, ठीक है, और हम आगे यहाँ पर. लेकिन ये तो फिडेलिटी की डेफिनेशन हमने नहीं ली हुई थी ना. वो तो मैंने सिमेट्री अज्यूम करके उसको उसके बराबर, हमारे जो डेफिनेशन ली उसमें रो सिग्मा रो था, वो मैंने सिमेट्री अज्यूम करके ही उसको फिडेलिटी के बराबर लिख दिया था. ओके, so any question about Ullman theorem? By the way, Olman theorem proves another property. which is not apparent from this definition or that definition, but it's apparent from the Olman theorem that fidelity must be between 0 and 1, right? क्योंकि हमने कह दिया fidelity is upper bounded by the inner product between two pure states psi and phi, and we know that the inner product can maximally be 1, right? So it means the maximally 1, and it is 0 only when psi and phi they are orthogonal. Bilkul, that's our next topic. That is there any relation between these two these two distances that we are talking about? But before that, I want to prove another theorem, and this is a quicker one, hopefully. Okay, and this theorem has a counterpart in trace distance as well. We say that fidelity is a lower bound of classical fidelity between two probability distributions that are generated by POVM measurements EM. Usme we showed that the distance was an upper bound over the classical trace distance of the probability distribution. Yahan pe it's the lower bound. Lower bound इसलिए है कि sort of fidelity, measures some a quantity which is sort of opposite to what distance trace distance measures. So when fidelity is 0, that's when the states are maximally apart. They are orthogonal to each other. And fidelity is 1, that's when the states are identical. We can actually see it from here. If rho is equal to sigma, ये क्या बनेगा? If sigma is equal to rho होगा तो ये sigma की power 1 है, ये half और half मिलके 2 हो गया. So sigma square root से गया. So trace of sigma is 1. Yeah, rho भी लिखने trace of rho is 1. All right, so let's prove this thing, and let me just repeat this thing, that the POVM measurements are those where these positive operators all add up to 1 identity, and PM is the trace of rho EM, and QM is the trace of sigma. So these are measurement outcome probabilities corresponding to these operators. Okay, so let's see the proof quickly. So proof comes from polar decomposition again, and for that, let me note that I can write some operator A as some JU, where J is a dagger. So using this polar decomposition, I can write this operator. Let's say this is my operator A. So इसकी polar decomposition होगी इसका square root. So उसके लिए I need this thing. Then it's dagger. इसका dagger sigma इधर आ जाएगा. And then some U, which means that rho square root sigma square root is rho square root sigma rho square root some U, or if I bring this U on the right side here, so this becomes some U prime. First करें कि U का inverse जो है, it's some U prime, which is actually U dagger because it's a unitary. So I multiply it on the right side, so I get U prime here. अच्छा, ये मैंने लिखा है rho square root sigma square root. You might be tempted to say, okay, why not write it rho sigma square root? But you can't do that. Okay, unless they commute with each other. Did he? यहाँ पे I just wrote a polar decomposition of this operator. Okay, and the definition of polar decomposition is this: A is some of positive operator J times unitary, where J is given by this. So let's say this is some operator A. तो इसका positive operator ये बन जाएगा A dagger times some unitary. Okay, J के साथ, so it's already a positive operator. ठीक है. अच्छा, ये और ये मैंने किया इसलिए है कि I wanted an expression for rho prime rho square root sigma rho square root, क्योंकि इसका जो trace है I know that that's the fidelity. So this means that fidelity of rho sigma is trace of rho square root sigma square root u, क्योंकि this is equal to this. So इसका मतलब है उसका trace जो है it should be equal to this. And let me now introduce an identity here. So that identity I can write as em square root sigma square root u prime. Let's take the sum out. So this becomes trace of rho square root em square root sigma square root u prime. And now I can use the Koshi Schwarz inequality for Hilbert-Smith product, thinking of this as my A dagger, thinking of this as B. So this inner product is smaller than or equal to the inner product of A dagger A. So this is A dagger, and its A would be em this. And similarly, trace of B dagger is U dagger sigma em, and then B, which is em sigma u prime. So ये बन जाएगा em, और चूंकि trace है, it obeys cyclic property, I can bring this rho prime here. So rho square root is rho. So this is trace rho em. Similarly, ये u prime इधर आएगा, तो u prime dagger identity बन जाएगा. ये sigma prime इधर आएगा, sigma square root sigma. So em square root em. So this becomes trace of sigma em. And this is nothing but PM, this is QM. So this is the classical fidelity between the measurement outcome, PM, QM. And you see that this was an upper bound of the quantum mechanical fidelity. Which essentially means that जिस हमने trace distance में interpret किया था, that fidelity gives you a minimum bound, a lower bound for the classical fidelity between two probability distributions, where each probability distribution comes from the corresponding measurements on the state. So आप एक state को measure करें, you'll get a probability distribution. दूसरी को measure करें, get a probability distribution, and then उनकी जो fidelity है, that's always going to be greater than this thing. So it's essentially telling us the physical significance of this number fidelity, quantum fidelity, because your classical sort of distance between the probability distribution is always going to be more than this one. Any question regarding this? We'll take a break after the questions, and then I have to answer one question जो किसी ने पूछा था. कौन सा वाला बोला कि इनका रिलेशनशिप क्या है, जो ट्रेस डिस्टेंस और इसके फिडेलिटी क्या है. And then we will see how we can use fidelity for dynamic distances between channels. Pure state को. हाँ. नहीं, पहली बात तो ये है कि ऑपरेटर्स भी तो मल्टीप्लिकेशन ही है. दूसरी बात ये है कि लेट्स से यू हैव अ वेक्टर, उसके 2 3 4 कंपोनेंट है, एंड देन यू हैव अनदर वेक्टर व्हिच इज अदर स्टेट. आपने एक वेक्टर को दूसरे में ट्रांसफॉर्म करना है, यू स्टिल हैव मैट्रिसेस, राइट? सो वर्ड ऑपरेटर और मैट्रिक्स इज द सेम थिंग. मतलब कैसे, लेट्स से एक 2 लेवल सिस्टम की स्टेट के लिए यू नीड लाइक 3 रियल नंबर्स और 2 कॉम्प्लेक्स नंबर्स. 3 रियल नंबर होंगे या 2 कॉम्प्लेक्स नंबर्स होंगे विद द कंस्ट्रेंट. 3 रियल नंबर चाहिए या 2 कॉम्प्लेक्स नंबर विद द कंस्ट्रेंट. ठीक है, तो अगर आप उसको उससे करते हैं वेक्टर से, सो यू हैव अ 3 डायमेंशनल वेक्टर, 3D वेक्टर. ठीक है, तो उसके लिए यू हैव 3 by 3 matrices to transform. So instead of 2 by 2 matrices, you will then be working with 3 by 3 matrices, right? So, or if you go to 3 level system, you quickly get out of control. दो कॉम्प्लेक्स नंबर चाहिए ना. ये देखिए, ग्लोबल फेज तो वो हम ब्लॉक स्फीयर पे रिप्रेजेंट करने के लिए उसको थोड़ी देर के लिए साइड पे करते हैं, बट इन जनरल टू स्पेसिफाई एनी स्टेट यू नीड 3 रियल पैरामीटर्स. हाँ. यार आप इफ यू डू रियली रिगरसली, एक ही बात है, कान इधर से पकड़े हैं उधर से. ठीक है, एंड people have worked many nights and many people over the world to come up with a better version of mathematical machinery to explain experimental results that are explained by quantum physics. So far everything runs into some trouble and no mathematical advantage of any other machinery is still known. तो मैं ये नहीं कह रहा कि हो सकता है आपके ज़हन में जो स्कीम है, it might be something that is useful, but something that you really need to work out and see its implication कि कहीं पे कोई फायदा हो भी रहा है या नहीं हो रहा. प्लस ये इस तरह की जो सारी स्कीम है ना, इनके डेड होने का एक सबसे आसान जो वजह होती है ना, वो ये होती है कि अदर देन मे बी 3 people in the world, nobody knows what quaternions are. ठीक है, तो आप 2 4 5 10 पेपर लिख भी दें कि इट्स यूजफुल टू डू दिस, एंड दे आर जस्ट somewhere in the far flung cabinet of some library, that's it. So जो लैंग्वेजेस जो मैकेनिज्म डेवलप हुआ है इन फिजिक्स को एक्सप्लेन करने का, लेट्स से जैसे इसमें देखें, इट्स ऑल लीनियर अलजेब्रा, राइट? So there are a lot of people who are very well familiar with linear algebra. Linear algebra is used in computer science, in physics, electrical engineers, many places. So somebody in electrical engineering decides to study quantum physics today. they won't have much difficulty. या क्वांटम फिजिक्स वाले उधर जाते हैं, कंप्यूटर साइंस में, इलेक्ट्रिकल इंजीनियरिंग में, वो आसानी से सीख जाएंगे. So whenever you come up with some new way of doing something, you have to keep in mind two things. Number one, is there a real advantage, which is not just, you know, that after a pile of books, another pile of books, you say, okay, this pile of book will create a hair of difference. It's little bit smaller than that. Who cares about that? So if there is, you know, ये 10 books लिखने की बजाय there you can say in a half a book, then somebody might be tempted to spend, you know, a year learning about quaternions or something like that, right? So first you have to demonstrate a sizable advantage of a new language that you are coming up, and then you also have to demonstrate equivalence. कि जो आप method use कर रहे हैं, it's equivalent to that. And usually equivalence is easy. It's very easy to come up with ways of saying the same thing, right? आप इंग्लिश से आप कहते हैं कि मैं एक नई लैंग्वेज जो है ना वो डेवलप करता हूँ, उसमें आई को मी कहेंगे, मी को आई कहेंगे, एंड एट द एंड ऑफ द डे ओके यू कैन से दैट, यू कैन से द सेम थिंग एज यू आर सेइंग इन इंग्लिश, जो आप अपनी जुबान में भी कह लेंगे. लेकिन 1 बिलियन लोग इंग्लिश बोल रहे हैं, तो व्हाई शुड दे लर्न दिस न्यू लैंग्वेज? गेट द पॉइंट? So let's meet at 6. चलो, आप में से किसी का एग्जाम तो नहीं है 6 o'clock पे? नहीं, अभी हो रहा है या होना है? मतलब तो 5 बजे खत्म हो गया होगा ना? वो रिटर्न है या ओरल? तो एक बंदे का 2-3 घंटे तो नहीं चलेगा, 5 बजे स्टार्ट होगा तो खत्म हो गया होगा. ठीक, लेकिन हम रिकॉर्ड कर रहे हैं, अगर किसी का एग्जाम होगा तो वी विल कंसीडर. जी